very much. So this is joint work with a lot of different people at Continuum and at academic institutions that we collaborate with. I'm presenting it, but the bulk of the library development was done by Jim Christ, especially all the parts that are really fast. Brendan Collins did all the GUI-related items. Joseph Cottam implemented the first version in Java, and we don't touch that version anymore, but it did pioneer some of the ideas, and Peter Wang was involved throughout in the ideas. So first off, anyone who talks about big data is obliged to define what they mean. I mean, is that 1,000 points, a million, a billion? And I take an operational definition of big data. Your data is big if there are too many data points for you to spend much time looking at any one of them. You can't really understand your data looking at your data point by point if it's big data. If it's beyond your capability of scrolling through a spreadsheet and looking at every one, then it's big data by my definition. And the thing about big data is that you can only understand it indirectly. You can visualize it, but if your visualization is misleading, suddenly you are going to say completely wrong things about your data set. And one way to know that you're dealing with this kind of scenario is that your visualizations aren't trying to really make sure each point is visible in the plot. They're trying to make sure the overall distribution is correct and faithful and accurately reveals what's going on in the data set. So to me, that's what I'm going to address. That's the type of data that we care about for this library. So this library is a standalone plotting packages may be overstating it. It's a library. It renders data into images. That's what it does. And it's not trying to compete with any other library. Well, there are a couple that have come up, but not trying to compete with Bokeh or Matplotlib. It's designed to work well with those. We're not trying to duplicate anything that those libraries do. Those are general purpose plotting libraries ranging from plotting 1 point to 10 points to whatever. But all the existing ones top out at a certain number of points. And Datashader is designed not to top out. And I'll show you how that could be. How could we not have a maximum number of points? And in particular, we work with the largest data sets we are able to obtain. So far, that's in the billions of points. There's nothing in the library that's restricted to billions. It could be trillions. We just don't have, it takes a long time to download trillions. So we tried it with billions. So if you use any standard plotting program, you try to plot a bunch of data points, your visualizations are going to be lying to you about the actual structure of that data set. In this case, I'm looking at a data set that I created, so I know exactly what's in there. And I'm just showing 3 examples of visualizing that with different plotting program settings. Which one of these is the real distribution? None of them are. So this particular distribution I generated from a sum of 5 different normal distributions. So I draw at random from 1 of 5 possible normal distributions with different widths. And I know exactly where they are and how big they are. And I know that A is completely misrepresenting it. That's due to a problem called overplotting. There are 50,000 points here, of which you can see a few hundred. So whatever structure there might be in this data set, you can't see that. But you can say, oh, well, that's because all the dots are too big. You can't fit 50,000 points in something that big, so let's make the dots smaller. So that's B, made the dots smaller. Okay, that's A distribution. That is something. And you can see their structure now. You couldn't see it in A. Is that the distribution? I don't know, because C is also a valid plotting choice. For C, I chose to enable transparency. That's another thing. If you've got a lot of data points, you can use transparency so that you can see, are there 5, are there 10? 5 and 10 points will look different. But whatever transparency value you have, it'll either do what's happening here, which is called undersaturation, which is when you have enough stacked up, it shows up as a dark color, but then you need several stacked up to see anything. And in particular, you can't see any of the points that surround this larger area. I know that there is a distribution there. There are 10,000 points surrounding all the ones you can see in C. You can't see any of them. They may as well not exist. In fact, what this is 5 different distributions, each one with 10,000 points. So none of these are more important or less important than the other. The one in the tiny dot, that's 10,000 points. The next dot up, that's 10,000 points. Don't have a pointer, so I can't point to those, but and that's doubly punny. But anyway, It's really important if you're trying to visualize big data that you have automatic methods that don't require on your human knowledge of the data, because you're using the visualization to uncover the properties of the data. And so you need something that actually is objective, something that can look at the data and then process it in an automatic way and reveal it to you, not something that reveals what you already knew about the data, which is all you can get from the first three approaches. And so you really have to take the human out of the loop, except for later. Later you can put the human in the loop to focus on certain things, to emphasize things. That's great. But for the first step, you ought to just dump the data right out to your visual system. It ought to accurately convey the data set to your eyes, to your brain. That's the whole point of visualization, and it's complete failure with most plotting packages, because they weren't, I mean, the style of plotting packages, they were designed to solve other problems when there wasn't big data, when you were happy to have 10 points. But we're not in that stage anymore. It's easy to get big data, it's hard to understand it, and that's what Datashader is about. And on the left is the default output when I just dump this data set to Datashader. We'll talk about how it comes about, but this is changing no parameters, it's just dumping it and let's see what it is. So we'll look at that in a little more detail later. So what is it actually doing? It's not, well, I don't want to disparage any field other than rocket science. It's not doing, anyway, it's doing something very straightforward. So if you have normal plotting programs, like non-Datashader plotting programs, you start with data. That's on the left there. And for instance, let's take bokeh as an example. I think a lot of people are familiar with that. And it'll come in later. With bokeh, you take your data, it's in some sort of data frame, and then you cram it into the browser, and the browser renders each data point as some sort of visible element in the browser. And that will work fine for 10 points, 100 points, 50,000 points, 100,000 starts to 1,000,000, your browser crashes. So that's not going to work for very large data sets. So instead, we have this pipeline that actually does all of the hard work offline, off-screen, and only the last step goes to your browser. And so this way, you start with the data, you figure out what you want to plot against what, and then you aggregate. That means take an arbitrarily large data set and turn it into a finite grid, usually the number of pixels that are on your screen. Even if you have a really good screen, the number of pixels is small compared to a billion-point data set. And so once you have it in that intermediate stage, the key is you can start to do computations on that stage. Now you can do all sorts of automatic auto-ranging, auto-discovering, auto-figuring out what this thing is that doesn't depend on the human, that depends on the properties of this data set at this resolution, at this level of analysis. You can automatically do all sorts of things. And then, when you're done doing that, you turn it into an image, you pass that to your plotting program, and that's what you see. So that last step, that image, all the first steps could have been in a remote server somewhere, could have been data center, doesn't matter. The only thing that needs to go from to the browser and therefore to your eyes is that last image step, and that image is fixed size. So you can take whatever you can do to handle the data. The data doesn't have to be in memory all at once. It doesn't have to be on one machine. You just have to somehow aggregate it, and then it can eventually turn into something you can see. And everything that happens every step along the way, by default, is designed to reveal, and also to give you power to control and to focus and select and so on. But the defaults are reveal, and then you have a lot of options, a lot of things that you can do. And of course, this is a Python library. I suppose I should have mentioned that. But all of the hard work is actually done in your native machine code. I think I had, yeah, that's the next point, which is this is a pure Python library, very small number of lines of code. It is not a burden for us to maintain this library. And that's because Jim Christ created really beautiful connections to Numba and Dask that will help, that translate it directly into runnable machine code. It runs super fast, runs really well. You write a small amount of code and it gets offline, turned into something that works well. And everything I'm showing you today was run on this particular laptop. You can use it on really big systems. It helps, but everything works here. So the things that we currently have addressed, these are just the things that we've looked at, are scatter plots of billions of points, which basically turns it into a heat map, looking at many overlaid time series, like If you have 1,000 or 1,000,000 overlapping one-day lines or very long time series without any downsampling. Downsampling is the devil. You are getting rid of your data. The idea is to reveal your data, not to throw it away. So there's no downsampling involved here, except at the very last sense in this. You have only a certain number of pixels on your screen. There's downsampling in that sense. But there's no downsampling in the sense that data is thrown away before analysis. And then connected points for trajectories, GPS-style data. We handle rasters, but kind of in a special way. We basically re-rasterize anything using rasterio so that we can combine it with any of these other data types. So it's not as if your data has already, basically this library is a rasterizer. So if your data has already been rasterized, all we can do is re-rasterize it so you can combine it with other data that has just been rasterized. But the final result is not just an image. It's an image that you can embed, and for instance, we show exactly how to do it into a bokeh plot to provide, to reconstruct the interactivity that you've lost by pumping it out into an image. So now I'll just switch, everything else is notebooks. That's just background. The rest is all demo. Nice to have more pixels in this room than the ones downstairs. I need them. Okay, so how to use Datashader? Well, first I'll very briefly show how to use something other than Datashader to plot it with downsampling using a standard approach, and then show Datashader. So first you get the data. At the moment it supports data frame-like objects. So it could be a pandas data frame, it can also be a Dask data frame. And Dask data frame allows you to work out of core, it allows you to work distributed fashion. As long as it's an object that implements the data frame interface, then we can use it. So this particular one is just a regular pandas data frame. Here we're loading the standard taxi data set, lots of people have seen. The only compute-intensive step here is loading, because it's just a CSV file. So that took us 20 seconds. And then we have about 12 million. This is only 1 month of the data. It's 12 million. It's our easy example. And if we try to plot that using bokeh, it doesn't take all that much code. Here's the plot of 1,000 random points. So this is heavily downsampled. The data set has a lot more structure than this, but any plotting program can handle a plot like that. This is just to show you how these are New York taxi, actually I don't, these are drop-offs. So then we try to push the limit. Let's take there's 10,000 points. You can start to see a little more structure. Maybe you can see some lines in Manhattan for the street grid. Okay, now 100,000 points in bokeh. For that, I turn this into an image because it usually works. But it often lets you not run anything else in the browser because it's really stressing out the browser to put that much data into it. And that's still ignoring 99% of the data. And it's already, things going to a halt. You can start to see really cool structure. Okay, well, what if we use Datashader instead? Notice this plot. Well, this one took a second to do with 10,000 points. The 100,000 one, I don't have the timing information, but it was it was tens of seconds anyway. If we go back to the Datashader version, in a half second it'll generate an image with all of the data points. This is the code that's involved. You can actually read it. There's not much code because it doesn't have much, the user doesn't have to do much. There's not much control that you have to exert. So you import some stuff, and it's basically 3 steps. One, you just declare what size area you want in data coordinates and in screen coordinates. So that's just a declaration. Then you aggregate using this canvas that you just created, and you say that use this data frame for my data, and I'm going to look at this column, and what I want to do is count how many passengers there were total. This is my aggregation. So an aggregation, what it basically is for every pixel in your final plot, what does that pixel represent? In this case, if it's passenger count, it means the total number of passengers for every drop-off that landed in that pixel. So the drop-offs are distributed across the entire geographic space. Some of them land in that pixel. Per pixel, just count how many drop-offs there were. That's what you're plotting. So that's aggregated. This is an X array at this point. So ag is an X array, and anything you can do with an X array, you can do with ag. And one thing you can do is plot it. So what we do here is we just say we want to interpolate from white to dark blue according to the passenger count and do it linearly. And this last step is very cheap. This whole thing only took a half second, but this last step is particularly cheap. Anything after aggregation is very, very cheap because it's down to a small number of total data points. So this is your result. It's not very impressive. And that's because of this hotspot right here. You're trying to linearly map a number of counts, but the number of counts in this one little part of Manhattan is very high compared to everywhere else. So you probably don't want to use a linear mapping because that's throwing away a lot of the bandwidth that's available for conveying data to your visual system. Really, you're just conveying there is a hotspot. But that's kind of binary. You've got a lot of pixels. You're wasting a lot of pixels to convey a binary idea that there's a hotspot. So let's do a little better. Do a log mapping. You start to see more structure. You can actually use a principled method where you equalize the histogram of pixel values so that there's an equal number of all different shades of gray in this case in the image. And that turns out to be a standard default way to reveal everything. And I'll show you that in a minute. And notice this is just giving you an image. You run this call, it gives you an image. But that's not very interactive, so you can embed it in a bokeh plot. All you do is write a function that creates an image and returns it. It's exactly the same pipeline you just saw, but all it does is when given a requested range and size in pixels, it'll return an image. And you pass that to this function here. You give it a bokeh plot, and you give it this function. So this function is only about Datashader. It's not about bokeh. But if you pass that function to bokeh, it'll give you this. In this case, I chose a different color map. Now you've got an interactive plot where you can, if you see something interesting in the data, you can zoom. And this actually, one more, I saw a face out there. Philip actually implemented this one, Philip Rudiger. He's not on a list of authors, but he helped out on this one. So this is effectively allows you to, so none of the data is being thrown away. It's all being aggregated. And so it's all there. In fact, we haven't actually implemented any of the optimizations you might do. So any of this zooming in, this is all using the entire data set from scratch. There's no caching, there's no tiling, there's no partitioning, there's no quad tree, there's none of the things that you could do to make it faster. It's just that the underlying algorithms are so fast with Numba that you can just handle data like this and you don't even have to do anything special. So here eventually you get down to individual drop-offs and you can explore them to your heart's content. But that's still just dumping it to the screen. What if you want to do the computations I talked about? Because it's an X array, you can do whatever you like. So here we created an ag, that's an aggregate array, that's an X array. But now let's just say we want to only plot the ones where in that they're the 90th percentile of pixels. And you want to do that every time you zoom in. So your first one, most pixels are empty, so you show all the data. But then if you start to zoom in, it'll focus on only the brightest bits at each point. And this is the sort of calculation you can only do when you've made the whole pipeline available for computations. Because this is not a computation on the data. These are not 90th percentile in any aspect of the original data frame. They're 90th percentile in this plot, at this resolution, per pixel. What are the 90% most hot pixels? And that's the ones that are shown. And eventually you'll get down to individual trips again. Similarly, you can take, you can combine multiple aggregates. In this case, let's compare pickups versus drop-offs. Each one of these is an X array, so one for pickups, one for drop-offs. And now let's transform them using X array. let's just drop all the ones where we're going to, sorry, not using X-ray. This part is using X-ray. Let's just color all the ones where the pixels where there were more drop-offs than pickups. We'll color those blue. All the ones where there were more pickups than drop-offs, we'll color those red. And the ones where they're equal, they're ignored. So if you do that, then immediately you see this structure that is clearly present in the data. For instance, if you look at the airport, there are well-defined pickup and drop-off regions. So you know those are only going to be the ones. And you can really see that the pickup regions are in the upper levels, close to the GPS satellites. And the other ones are down below, therefore a very bad signal. You can see that coming through extremely clearly. You can also see that where are you going to find a cab in New York? Along the thoroughfares and along the north to south routes. The side routes are where you get dropped off. So they're in blue on average. And you can uncover lots of structure like that just by interactively zooming around and seeing what you see. And again, you always have all the original data points. They're all there. They've all fed into your display, and you can reveal them whenever you want to. And again, this is every time you zoom, this is all 12 million data points being processed with no, we could have easily made it be super fast to zoom in just by eliminating the rest of the data set, but we haven't needed to because it's fast enough. Here's another example, same data, color it by hour. This is really, really cool if you knew anything about New York. I've never been to New York because many times as I've been through it on a plane, I've never gotten off, so I have no idea what are these things that people do at certain times of day in New York. Somebody knew what's going on here, like what is that? There must be some event that happens every day that people need a taxi to go get dropped off for whatever that is. I found one of them that turned out to be, it's the taxi licensing place, so you have to check in at certain times of day if you have a taxi. So that actually stands out pretty clearly. I think that one's right here. Oh no, it's that other one. This big spot over here that's all in one color. Apparently you have to drop off at the beginning of the day you have to do this, and at the end of the day you have to do this. So there's lots of fun that you could have exploring this if you knew New York. I know, and this is all geographic data. We could do the same to explore other things. It's just not very visceral to everyone because people can immediately see geographic. If it's other non-geographic, it's harder to understand and make sense of. Here's the same data set where we plot distance of a trip versus the fare, and you can easily see a linear relationship. That's part of the law. I mean, the regulations say that there will be such thing, but then there are all these things down here. What are these? A 15-mile trip for $2? Those are some sort of error, right? And all this data out here is errors. This is something the taxi companies could easily study. And again, you can, if you enable the zoom, you can explore it. You can also see the discretization as you zoom in. This is discretized data. Why? I don't know. Why would it be discretized to 50 cents? Sometimes. I don't know. That's what's in there. We can do the same thing with census data. Get lots of pretty pictures out of that. This is the 2 lines that you need to start, and then you need 1 more to plot everything. The first one this is 300 million points, took 10 seconds. The rest of them all take under a second. Here's a linear. You see, oh yeah, there's New York and LA. Okay, so don't use linear. Skip that one. This is log. Now you can see a lot of structure. And this is the default, which is just do histogram equalization, show me all the data. And by default, you just pump this in. You don't do some months-long research project. You just dump it in here. There are no parameters this is all the default settings, except for choosing the gray color map. So I chose to do it in gray. You choose whatever color map you like. But now we can do computations again. Like let's say, okay, well the gray color map is great, but it doesn't reveal those hotspots we saw in the first one. Okay, well let's color the top 1% of the data, make it red. No problem. Now we see all the cities in America, all the Chicago. We're right here. Austin is worthy of the top 1% of dense pixels. So we can This actually has racial data. We can colorize everything by race. This is a bunch of whites. We're down here. There's a little stripe of Hispanics running through the middle of Austin. On east of I-35 is Hispanic, west is white. Blacks throughout the south, but we can zoom in. For instance, if we notice that there's something might be going in Chicago, let's zoom into Chicago. We can see, oh, there's some structure there. Keep on zooming. Again, this again is the default. All I did was assign a color to each category using this list. There's no other parameters were tweaked. There's no adjustments necessary. This is the data. Stark as it is, people don't like to live next to each other. This is Chicago. That's Chinatown. The north side of Chicago, whites live there, not in other places. It's very disturbing. Keep zooming in. This is Chinatown, and Chinatown is very Asian. Red means Asian, but across these are actually freeways and railroad lines. Across there you have Hispanics. This is just a street. You have to cross the street if you're black, apparently. It's ugh. You don't want to see this data, but it's real data. This is New York for race. I could keep showing you as many pictures as I want. The last one that I'll show, though, is one that this is all the pixels, well, two pictures. One is, this is all the pixels where there's somebody from every race in that pixel. So this is basically cities. And these are all the pixels where there are more blacks than whites. So black neighborhoods of major cities, Hispanic neighborhoods of LA, and rural areas in the South. And this is kind of unpleasant data to look at. I mean, it's really astonishing how segregated we are down to the individual block level everywhere you look in America. It's just revealed. So anyway, stop there.
Questions?
Do you have a way to show legends?
Yes. I don't have time to go into everything, but you can show legends, you can show hover information. This is all stuff that you backport onto it. So the bare library gives you an image, but it's an image that's situated in some coordinate system, and you can, for instance, for hover information, you just re-aggregate at a lower resolution, and then when you hover, you get the stats for that little box that you've aggregated. And the same for legends, you just show what you pass in the data range through the same functions that we're showing here. It's basically you have to work to get things that were free in Bokeh. But you can do them, you can just re-implement them from the other direction. Since you've lost everything by doing it to an image, you have to re-implement interactivity, you have to re-implement legends and things like that. But we've done that work for Bokeh. You could do the same thing, that work for other libraries. I'm on the Bokeh team, so I've done it for Bokeh. But you can do it, that part is not that much work. The core library supports any library.
Is there any difference in the result if it's red on top of blue or blue on top of red?
Red on top of blue in a categorical case.
So I mean, with
Matplotlib,
the order in which you plot things has an effect on.
That's right. So overplotting. So in the case where I did drop-offs versus pickups, no, because I chose if it's a binary switch. If it's more pickups than drop-offs, it is always blue. So those are two completely disparate images, and they're basically combined and not overlap. You can do whatever you like. In the things that are built into the library, overplotting doesn't occur because there's no sense in which data is presented in order. Data is aggregated, and you get the result. So the aggregation is agnostic as to order. So we do our best to handle that in everything we do, and it's up to you to handle it in the stuff that you do, because you have full flexibility once we've given you that array.
So hover, I can see quite straightforwardly how you do it. Linked brushing seems a bit harder, or am I wrong?
Well, you can link by aggregation. So basically, you can link by grid. So if you hover by grid, you can also drag a lasso and select by grid. And you can't select by points, but you can select by a grid that contains points. The same thing. And that comes back to the whole premise of the talk, which was you're starting with data where you're not going to do one by one clicking on points. You're going to have to aggregate it in some way. You're going to have to treat it as a distribution, and the same applies here.
So since you have to calculate the entire data set when you like
We don't
move to
have
a
to,
new-
but we currently are, yeah.
Right. Well, since you do, when you zoom, you have to re-aggregate and redo that calculation.
The entire pipeline is rerun from the start, as if it has zero knowledge anything has ever started. That's not a recommendation, it's just, it's the first thing to do, the easiest thing to do, and so far it's been fast enough. Oh, I didn't even show it. The next data set I would show would be a 3 billion point data set. It took a minute and a half to render that on this laptop, but if you use Dask, you can get it in a second or so across the cluster. Or we could probably get in this on this laptop much faster by pre-computing tiles and dividing up the data set and that sort of thing.
So is the speed different if you zoom versus pan? So if you pan
No.
through, it already
It's all
has-
redone from the start.
Okay, so it redoes the whole thing and then just creates an image from the
That's
range
right.
that you're looking at.
It goes right back to your full original data set. Again, we don't have to do that. It's just that's what we do, and it's easy.
Okay. Yeah, that's awesome. Well, thank you.
Yeah.
So could this sort of thing be used for something where you compute the data set each time instead of having it all at once?
You mean a synthesized data set?
Yeah, or like say you want to use this to like zoom in on the Mandelbrot set or something silly like that. Like you don't.
Yeah, I suppose. If you have a way to compute the aggregated value without the underlying values, as you do for a Mandelbrot set, because you're iteratively refining it, you could certainly, it would be interesting to connect it to something where you're iteratively refining in that way.
So it's break now, but if people have a few more questions, we can probably take some.
Go have a break.
Okay. Thank you.